Okay, well, I will get started. Let me begin with a word of prayer. So, Heavenly Father, we thank you for your creation. Thank you for this day, for this class. Just ask you to bless our work today. Help us to glorify what we do, and help us just understand a little bit more about potential and electrostatics. Lord, in my prayer, Lord Jesus. Amen. So I should probably review what is a conservative force, right? Because that's kind of the issue here. So let's talk a little bit about conservative forces. So a force is said to be conservative if we can write F is equal to minus the gradient of a potential energy function. So what's a gradient? So a gradient, this looks like explicitly something like, minus partial u partial x minus partial u partial y minus partial u partial z if we're in 3D, right? If we were in 2D, then we just have two components there, right? So this is the gradient of the potential energy is the force. That's what we mean by a force being conservative. Now, so here u is the potential energy function, right? Now, the potential energy function's not unique, right? So if you look at those derivatives, if we added a constant to u, none of the derivatives would change, right? So for a given conservative force, there are infinitely many choices of potential energy. However, once you fix where the potential energy is 0, that pretty much fixes your potential, right? So it's not unique, but it's also pretty easy to tame in that regard. So there are various ways we can understand what a conservative force is. Like, what are the properties of conservative forces? And so, here are the properties of conservative forces. Just briefly, the properties of a conservative force are like number 1, F is equal to minus the gradient of the potential energy. That I take that to be the definition, guys, right? But point number 2 is you have path independence. And by that, what I mean is that if we were to calculate the work done by the force along one path, say C1, and if I was to calculate the work done by the force along another path, C2, all right? So this is work done along C1. This is the work done along C2. Well, we get the same work, all right? So path independence says that if you calculate the work done by that force between two paths, like these are coterminal paths, right? So like imagine the picture is something like this. We go from point P to point Q, right? And so these two paths, they've got the same, starting and ending points, okay? They're coterminal. So this is path independence. 3, you have the integral, the work done by a path independent force around a loop is what? 0, right? It's 0. And then 4 is a little bit more technical, but for the domain of the vector field simply connected, we have the curl of the vector field is 0. So now I'm getting a little bit further into the Calculus 3 weeds, so to speak here. This is something you should learn towards the end of Calculus 3. You might not know about this yet, and that's fine, all right? But there is something called the curl. You can calculate the particular, kind of like a determinant slash mixture of partial derivatives. You'll learn about it in the last 20% of Calc 3. Some of you aren't there yet. That's okay. This is not required. I'm just giving you the full story here. So these are actually not just properties, these are equivalent characterizations of a conservative vector field. If I logically give you one of these, I can prove that the other things are true. So this is actually a list of equivalent statements in the context that the domain is simply connected, which means that, sorry, eventually I'll learn how to mute my phone. It's my mom, so. What's that? Oh yeah. So I mean, is answer to prayer. It's a good thing. So so anyway, the point is you could prove that these are equivalent in this context. Now, simply connected means that the domain doesn't have like a hole in it. Basically, there's nothing you can get stuck on by deforming a loop. You can take a loop in the domain and deform it to a point. What's not simply connected, for example, if you take the plane and punch a hole in it, that would be an example, like the quintessential example of a space which is not simply connected. Or you could take 3 dimensions and remove a whole axis from it. That would not be simply connected, because there's no way you could deform a loop that was around like the z-axis to a point. You get stuck on the z-axis if you're missing it. Anyway, these are equivalent characterizations of a conservative force. And one of the things you work out in Calculus 3 is that if you have a conservative force, you can actually build a formula for the potential energy like this. You just say U of r is equal to like minus the integral from say r naught to r of f dot dr. So you could define the potential energy function from this integral. Now in physics, excuse me, in Calculus 3, I don't put a minus there because in Calculus 3, we don't care about energy. We just think about, you know, like the conservative vector fields, the gradient of a function. We don't put the minus in because it's not physics and we don't care about energy. But in physics, we care about energy, which is why we put that minus there, as I'll explain shortly. But I want to point out to you that the proof of the equivalence, basically it rests on this thing here, that if you have path independence, then I can build the potential energy by this integral. All right? And then you can prove, through about a half hour of calculus, that when you take the gradient of this formula, you get back f. It's a lot like, it's sort of the multidimensional analog. Do you guys remember from Calculus 1? Everybody's had Calculus 1. You know this, right? d dx of the integral from a to x of f of t dt. How's that go? I usually call this FTC1. Do you guys remember it?
Just f of t.
F of t is close. Trade that t for a x, right. So this is FTC1, which rarely appears outside of Calculus 1, right? It appears in optics if you define something called the Fresnel. There's like a function that involves an integral of a particular thing. So it does come up in applications in physics and places, but anyway. My point to you is like, that's kind of the multidimensional analogy of this is what I'm talking about right here. Because what I'm saying is that if you take this formula and you calculate, you know, minus the gradient of u, you will get f. That formula implies that, all right? This I prove carefully in Calculus 3. I'm just telling you it here. So what that means is if I want to construct the potential energy function from a given force, I just have to calculate that integral. Right? So we could do that, for example, for the Coulomb force, right? We could work this out. Now, what's R naught? What's the deal in this construction? Like, what's U of R naught equal to? What happens if you calculate the work from R naught to R naught? Yeah, it's 0. So basically, R naught is the place where you define potential energy to be 0, whatever that would be. So it's actually a little bit weird what we do in here with regard to physics. Let me not lead with that. We'll get back to it. Okay, so this is just a brief overview of what is a conservative force. Now, why do we put the minus in? What does this have to do with conservation of energy? Let's look at that. So I will eventually return to that, and we'll derive the potential energy for the Coulomb force. But first I want to get back to energy here. If we have the force is equal to, minus the gradient of the potential energy function, right? And it's also equal to ma, then what's the story? This is what? This is like m dv dt, right? So let me work it out. So suppose we're calculating the work done by the force, all right? Say from, I need a notation here. I want to go, say, from a point 1 along some path over here to some point 2, all right? So like imagine you're calculating the work done along such a path. It begins at point 1 and ends at point 2, okay? So there's two ways I can go down here. Let's start out with using its conservative. If it's conservative, this is minus the integral of the gradient of the potential dot dr, all right? And fine, I'll write it again. So we're going from P1 to P2. All right, great. Well, there's a theorem that the integral of a gradient is simply the difference. So what the theorem here is that is u of P2 minus u of P1. Right. So you could say that this is minus the change in the potential energy if you like that kind of notation. Now, if you've had physics with Dr. Budara's here, you've not seen that notation because he does not like this notation. Like a lot, from what I understand. But I learned this notation in like community college, so it has a nostalgia for me. PE for potential energy, right? It is weird though to use P and E for the domain, for the name of a variable, right? Like we don't do that much. But PE is equal to U, all right? Now, that's one way we could do it, but the other way we could do it, right, is that the work done from point 1 to point 2, what would it be? What's another way to look at this? Well, if it's the total force, right, we only get to say this if it's the net force, right? Only the net force is equal to ma. But if it is the net force, then this is also equal to the integral of ma, which I'll write as m dv dt dot, dr. All right? Now, let's see here. Let's work this out. How does that go? Like, what's the definition? How do you calculate the work done? So the way we do that is we say, well, that's really the integral from, say, T1 to T2 of m dv dt dot, dr dt. That's how we actually calculate that integral. Right. We look at the parameterization of the path with respect to time and suppose it goes from time 1 to time 2. That's actually how we calculate that. What is dr dt though here? That's what? That's velocity, right? The derivative of the position with respect to time is the velocity, yeah? So if you look at this, what we're really looking at, and now this is a little bit of a trick right here I'm about to write. This is actually ddt of 1/2 m v dot v. So what I'm doing is a little identity here. There's a product rule for the dot product. Those of you who are currently taking Calc 3 will have either just seen this or should see it soon. If I have ddt of like a dot product of two vectors, the way that works is you get dA dt dot b plus a dot db dt. There is a product rule for the dot product in this way. And so like if you look at the derivative with respect to t of v dot v, how's that go? Well, it's dv dt dot v plus v dot dv dt. But dv dt is the acceleration, right? So what is that? I mean, this is technically 2 V dot A, because the dot product is also what? It's commutative, right? So what I'm starting with here is V dot A or A dot V, right? I'm replacing that with 1/2 the derivative of V dot V. That's just an identity. And then what? Well, then this is the integral of a total derivative, but remember calculus 1, the net change theorem. This is equal to 1/2 mv squared evaluated, say, from time 1 to time 2. And of course, you might recognize that as kinetic energy at time 2 minus the kinetic energy at time 1. This equation that I wrote at the bottom is called the work energy theorem. It's true even when the force is not conservative. You see that second line, it doesn't use the fact that F is the gradient of a potential energy function. It simply rests on the fact that the force is the net force. If the force is the net force, the work done by said force over a path will be equal to the change in kinetic energy. I'm not losing any of you guys here, am I? Like V dot V is V squared, right? So this is 1/2 mv squared. Nothing much going on there. So you put these two things together, what you've got is that, up here I have, minus potential energy 2 plus potential energy 1, right? And lo and behold, if we put this and that, and we put them equal, what do we get? So if the force is equal to minus the gradient of the potential, then the energy, which is equal to kinetic energy plus potential energy, is constant. It's conserved, right? So we have that, I'll write it out in detail, 1/2 mv1 squared plus the potential energy at point 1 is equal to 1/2 mv2 squared, v2 squared, plus the potential energy at P2, right? And so, as you guys maybe remember, I think you remember from Physics 1, well, this is super, super nice, right? You can solve problems with conservation of energy. It makes it really nice, right? Energy was a wonderful method. What's the nice thing about energy as compared to earlier parts in physics? It stays well, yeah, it's conserved if the net force is conservative. I would say one of the nice things about energy is that it's a scalar, right? There's no vector here. Potential energy, kinetic energy, they're both scalar quantities. So that's good, because sometimes you guys have trouble with vectors, right? Yeah, sometimes. All right. So that's just a brief lightning review of what is a conservative force and why does it mean we get conservation of energy. Now I'd like to return to the topic at hand, which is electrostatics. I want to look at what is potential energy associated with, like, the Coulomb force. Can we make sense of that? All right. So I guess I should probably use the other board, huh? Duh. I do have a third board. Sorry, guys. You guys are over here too, right? What are you? Well, yeah. Somebody put that board up. I don't know, but who'd do such a thing? But here's the deal. Goodness gracious. There's just something funny about the potential energy for the Coulomb force that doesn't quite allow the direct calculation that I'd like to do for you. I guess I can, but let me just be specific. All right, so let's think about, let's calculate the potential energy for Coulomb force on mass m with charge q. All right, so let's see here. I'm going to put the source charge. Sorry, I've got a mental block at the moment. I'll put the source charge here. And I'm going to put we're going to investigate this one out here. This has the mass m, all right? So all right. I want to think about it three-dimensionally. So what's the force on this guy here then? What did we say it was? The Coulomb force is what? F equal to? How's it go? KQQ, right? Little q, big Q, divided by, what we got? I guess it depends on where we are, doesn't it? Let's put Q. I'll be really boring. We'll put it at x, y, z. Okay. So we've got what? We've got, you know. Let's see here. I guess I'll do x squared plus y squared plus z squared to the 3/2 power times x, y, z. Right. That's one way we could do the formula. Like problem 4 on the test. Right. So, although this is slightly easier, I put one of the charges at the origin, right? Just to keep things relatively simple. So what's the potential energy due to the electric force of big Q is really my question. I'm sorry. I need to think of a way to. Well, I guess we need to pick an origin for our potential energy. Where do you guys want to make the potential energy 0? You want to make it 0 at the origin? I think that's the one choice I probably can't make.
Just do 1, 0.
1, 0. So you might want to make u of let's say L 0, 0 equal to 0, because I don't want to write 1 meter. You can think L equals 1 meter if you like. I think I've dug myself a hole, though. I don't know if I want to actually do this calculation. It may be easier just to guess at this point. Let me show you what I'm up against. So I'm trying to figure out, you know, oh. So you guys tell me, what's the, oh, no, we're fine. I'm an idiot. So I just don't know where to put out my stupid picture. So I guess it's, if I draw it like this, the usual thing, x, y, z, right? Sorry, I do this. This z is that z, don't, yeah. But L00 on my picture would be somewhere in here, right? So can you guys tell me, like, what would a path be that goes from my origin for the potential energy, my 0 for the potential energy, in the place where I'm trying to figure out the value of the potential energy x, y, z? How can I get from this point over to that point? How about this? You know, just line segment, right? So how do you write the formula for a line segment from there to there? How about this? X is equal to L plus T times, you know, let's see here, X minus L. And Y is equal to Ty. Oh, my bad. Ah, rats. See, there's a different distinction between this x and that x. To fix this, let me slap some subknots up here to keep us from going crazy. So x naught, y naught, z is equal to t z naught. So right here, for 0 less than or equal to t less than or equal to 1, that is a parameterization of the line segment that starts at the point L00, which you guys picked, right? And goes to the point x naught, y naught, z naught. Try it out. Plug t equals to 1, what happens? You get L plus x naught minus x naught, minus L, which is x naught. Plug in t equals 1, y equals y naught. Plug in t equals 1, z equals z naught, right? What happens when you put t equal to 0? 0, 0, and L. Most of you are taking Calculus 3 or have taken it. You should recognize this as the standard trick for parameterizing a line segment from one point to another. If you don't, that's okay. Or is it? I don't know. I was talking to Dr. Schmidt. He said you guys are doing awesome. I was talking to Dr. Wang, and he's like, so I guess Dr. Wang got the bad students or something. I don't know. But anyway, so that's the parameterization. And so I'm trying to calculate, believe it or not, f dot dr from my, let me call this thing r naught. Oh, I better not. Rats. Well, I'll just write it out, L00. And I'm going to call this point r up here to r. And you know, the way to do that, if you remember, is I can just plug in these, right? What's dx here? What's dy? What's dz? It's dt, I think. It's y naught dt. It's z naught dt, I believe. And this one was also not just dt. What was this one? If I differentiate this with respect to time, I get what? I get x naught dt. Is that right? My bad. That first one is x naught minus L, I think. dt when I differentiate it, right? Because that's the coefficient of t. So like dx dt gives me x naught minus L. dy dt gives me y naught. dz dt gives me z naught. All right, so you can look at this as like p comma q comma r, right? And this is going to give you the integral from 0 to 1 of p dx plus q dy plus r dz, all right? And then you could plug in the formulas we have here. Like if I do that, what's x squared plus y squared plus z squared? Ah, it is most hideous. Yowzers. Great, googly moogly. I do not want to calculate that. Permission to bail. Okay, good. So we could complete this calculation, and believe it or not, at the end of it, something relatively simple comes out. I know it's hard to believe, but there's supposed to be a minus here, right? That would be the potential energy at R. All right, so because I've done this to you, I will try after class, after everything else is done, before I fall asleep hopefully today, to complete this calculation in its insidiousness and post a PDF of it for you guys, okay? All right. Understand the question we're asking is just this. Like we're asking, if I have F is equal to KQQ over r squared r hat, right? That's equal to minus the gradient of what potential energy function? That's the question we're asking. Can we solve this right here, right? Let me show you a way to make this fantastically easier than direct calculation of this monstrosity. I'm sorry, guys. I should know better by now to not try to do that.
Remember the 45-degree collision problem proof from last year?
Is this the 40? I'm trying not to remember those things. So let's see here. So what you're talking about. So here's the thing, guys. The gradient of a function, on the one hand, you can write it like this. You can write partial f, partial x, x hat, plus partial f, partial y, y hat, plus partial f, partial z, z hat, right? We could do that. This is usually what we start with and pretty much all you ever do in the Calc 3 course here, right? But the truth is, when you're in physics and engineering, this is not what you often need. You often need the gradient in spherical coordinates. And in spherical coordinates, the gradient looks like the following. R hat times partial f partial r plus theta hat times stuff we don't care about plus phi hat times stuff you don't need to know about. But these involve derivatives with respect to the spherical angles, okay? And I don't remember them off the top of my head because, I don't know, for shame, I should know these things. But, or maybe I'm just not trying to burden you with what has never been in your education. Sorry, seems like that phrase is in my head now. But, so this is the gradient in spherical. So with that in mind, you're trying to take their Coulomb force, F, equals to, K, Q, over r squared r hat, and you're trying to equal r hat, well, there's a minus here because it's potential energy, like minus the gradient of the potential energy, but that's minus r hat, partial u, partial r, plus, think about it. Can the potential energy for the Coulomb force, can it involve the spherical angles? Think about it. It's impossible for that to happen because the Coulomb force only depends on the distance from the origin, right? So it can't have an angular dependence. The derivatives that I haven't even written down don't matter to us. The rest of this, it has to be zero by the spherical symmetry of the Coulomb field. So you see, actually all we have to solve is something much more simple. We just have to solve this, KQQ over r squared, I'll put the minus on the other side, equals to partial u, partial r. Now can you solve that? Can you tell me what u is if the derivative is that? Yeah?
Would it be you take the, just solve the differential and take the integral with respect to r?
Right, yeah, integrate with respect to r, that's all we got to do. So this gives me what? U is equal to what? We got ourselves a K, QQ over r. Am I right? How do you check? You're like,
You take the partial.
you keep writing these funny looking symbols. I don't even know what this means, right? What does this mean, this partial? For those of you who don't know, actually, is there anybody who doesn't know what I mean by partial derivative in here?
I'd like an explanation.
So it means to differentiate with respect to x, holding everything else as a constant. So, yeah. I mean, I can give you a definition in terms of limits if you really desire it, but you do not want a definition in terms of limits. No one does. Look, so if I differentiate that with respect to r, I get that, right? Because the derivative of the reciprocal function is minus the 1 over the square function. So that is the potential energy for the Coulomb field. Now let me explain to you why the direct calculation was troublesome, because this is our standard answer. What did I tell you at the start of all this? I said we could add a constant to the potential energy to make the zero wherever we want, right? where's the potential energy for this standard form of the potential energy, which is what I wrote there? Where's U equal to 0?
At R equals 0? Or
0 is not defined.
no?
See, that's the problem. I can't even put 0 in. The electric field is not defined at the origin.
At infinity.
At infinity, right. Yeah, the potential is 0 at infinity.
Other way.
Yeah. So it's hard for me to set up the integral that starts at infinity. And, I mean, I would have had to do that to make this calculation not so horrible. And that is what you do, actually. Instead of looking at a finite point, you take a point way, way out, and you just integrate back along the radial line to the point where you're coming from. And that's how that calculation becomes less annoying. But it is weird that the potential energy is 0 very, very far away. Which direction very, very far away? The answer is yes. Every direction. If you want the potential energy to be 0 somewhere finite for this, you have to add a constant, right? If I add a constant, you know, whatever here, C1, that would make the potential energy 0 somewhere else, perhaps. Are we good so far? I'm sorry for the detour and the failed calculation. I'll try to make it up for you with punishing myself to do the calculation later. So what is this course about? This course is about electromagnetism, right? And so we're right now talking about the electric part, electrostatic part. And so many of you are, at least some of you, how many of you are electrical engineers? So what do you guys care about? Do you care about electric fields?
Yes.
You do?
Deeply.
What else would you care more deeply about it than electric fields?
Very little.
What about voltage? Right? What is voltage? What's that? AC/DC. Oh yeah, we'll get there. But we're dangerously close to the concept of voltage. So the deal is this. So here, this was all for what? This is all for like a point charge Q at the origin, right? So this is the potential energy due to Coulomb force from big Q, right? But you notice something, that is what? That regards like a little test charge out here, you could think of it, at R, right? And what did we define? We defined the force, right, is equal to the test charge times the electric field, right? So we introduced electric field in the last story arc of the course, and it was the force divided by the test charge, right? So electric field is Coulomb force per test charge. That's the way we could think about it. The analogous concept here is voltage. So the voltage, V, is equal to the potential energy per test charge. And so this is why we say the voltage, or the potential function, as we usually say in this course at this point, is K big Q over R. That is the potential. And when we say potential here, we don't mean potential energy. We mean potential energy per unit charge. That is the voltage due to the charge Q at the origin. All right? See if I have time to do something. Yeah, I have time. You might be like, oh, okay, well, so what? Well, let me try to redeem this lecture by showing you a non-trivial example. Although if I was smart, I'd probably just turn back your test now. Let's see here. Oh. Now seems like a good time to mention, I do drop the lowest test grade and replace it with the final exam if helpful. That's definitely relevant to some of you, many of you. So check this out. Example 1. If I put Q1 here at, say, the point x1, y1, z1, and I put Q2 over here at the point x2, y2, z2. The way this works, if I want to know the voltage from both of these together, guess how it works? It's amazingly simple. You do V is equal to KQ1 over the distance to 1 plus KQ2, let's say over the distance to 2, where I probably should use the script R's here. That's been my notation up to this point. So we want to find the voltage over here at a point x, y, z, right? So the script R's are the distance from the source points to the field point. Here's my script R1. Here's my script R2, right? So the voltage is actually just, KQ1 over the square root of x minus x1 squared plus y minus y1 squared plus z minus z1 squared plus KQ2 over the square root of x minus x2 squared plus y minus y2 squared plus z minus z2 squared. I will prove these things in a little bit more, with a little more care in a future lecture, but we do have this additivity of voltage functions. And this is super nice, right? Because what's the electric field, by the way? Notice how this works. If the force is equal to Q times the electric field, right? And it's also equal to minus the gradient of the potential energy, right? And notice that that is what? Minus the gradient of Q times the voltage function, right? See, because my V is U over Q, so U is equal to QV, right? U is equal to QV. So what happens? See this Q here and that Q here? You can cancel them, and we get the simple rule. The electric field is minus the gradient of the voltage function. You might not be impressed. You might be like, you just replaced something I don't understand with two things I don't understand, so what do I care? But no, you shouldn't look at it that way at all, because I've just given you license to not add vectors. See, all you have to do to find the electric field here, right, is calculate the gradient of the voltage function above, and that's the field. Whether or not you know how to add vectors or not, if you can calculate derivatives of a voltage function, you found the electric field. That's very nice, because we can just add scalar voltage functions and then differentiate to get the vector field. That's very cool. And I mean, I know the calculation, I don't have time for the calculation, right? But it's straightforward how that goes. I'll write down the first thing. I'll put the minus, and I'll put a K out front here. So you'd have like, Q1 over, I guess I could talk about partial R1 partial X is actually equal to, if you look at it, 2 times x minus, let me not start down this path, guys. I'll do this. I will do this calculation when I have time, which is not today. Let me not start this. I'm sorry. I should have just stopped where it was good, which is right here. Beep, up, done. All right. My apologies. Let us conclude the taped portion of today. I want to give you guys back your tests, and I am also redoing the teams. So the teams have been reassigned.